Hi, in this video I will show you how you can use a certain kind of flip-flops in circuitverse for storing data and how to use a clock to sequentially move this data around. Under sequential elements you actually can find more than just one flip-flop, but I will use this what's called here a D-latch. Now let me show you how to use this kind of flip-flop for storing data, a single bit. I will use two inputs and one output. The inputs here on the left hand side are called D, that's this one here, and the other one is called clock, and the clock has a special marker because it has a special meaning. With this D input you can specify what data should be stored in the flip-flop if the clock is equal to 1. So let's call this here D new data. And this other one I simply call clock. And here on the output side you see you have here Q and here Q inverse. That means this lower input is always the inverted value from above. So I actually will just use this upper output port. And you also see that inside of this flip-flop box you see what value is actually stored inside of this flip-flop, and that means what you see here in this output Q is always the stored data. Now if you want to store data you can, for example, specify that I now want to store a 1 in this flip-flop, but then you see nothing changes. That's because the clock is equal to 0. And with the clock you basically can control whether new data flows inside of this flip-flop or gets copied into this flip-flop or not. You can enable or disable this storing facility. So if I now change the clock from 0 to 1, you see that this data gets copied into the flip-flop. If I now turn the clock back to 0, I can change here this new data, but it has no effect of the data that is stored inside of the flip-flop. And of course you can describe this behavior with a truth table, but then you will see on the truth table you actually have 3 inputs, because what is stored not only depends on D and the clock, it also in general depends on what is already stored before. But describing this flip-flop more formally is something we can do in class, or what can be covered in another video. Here I just want to focus on how to use flip-flops for storing certain things. And then of course here let's also see that I now want to, for example, store a 0 inside of it. It simply means that I have to turn the clock to 1. Now I have this data flow, then I close this input here, and then I can change it again. So here, just by example, you see how I can store 1 bit of information in a flip-flop. And of course you can use 2 flip-flops for storing, for example, 2 bits. And you simply can do this by explicitly using 2 flip-flops. Then I would have input field with 2 bits. So I change this to 2 bits. I also will call this D new data. Then I can use a splitter for splitting 2 bits into 1 and 1. And then I can do the following. The most significant bit can be stored in this first flip-flop, and the least significant bit can be stored in this second flip-flop. And then I simply copy this splitter, change the orientation to left, and for seeing what is stored in these 2 flip-flops, where I want to show it as a 2-bit result, I simply assemble this 2 bits. Let's rearrange this. The most significant bit I get from this flip-flop and the least significant from here. And then I again need a clock for allowing to move the new data into these two flip-flops or disable this writing. So I will connect the clock with both flip-flops. Okay. This actually doesn't look nice. Let's do it like that. And now you see I can store, for example, 1, 0 by turning the clock to 1. And here you see the stored data, or 0, 1, or of course 1, 1. And of course with 3 or 4 or more flip-flops you can store more bits. Now by knowing how to use several flip-flops for storing more than just 1 bit, I think it's okay to simply use a feature from circuitverse that you also can simply change the bit width of a flip-flop, for example to 4 bits, and this just saves a lot of time. Now I simply can use a 4-bit input field and a 4-bit output field. I don't have to do this splitting and connecting of single bits. And again, I simply have 1 bit for the clock signal. So that means this box here is simply hiding something like that, where you actually do have 4 flip-flops. And the advantage, of course, is that if we do examples with 4 bits, we can use hex displays to represent the bits more compact. So for example, if I want to store hex F in this flip-flop, then you also see here circuitverse displays the stored value in hexadecimal. You can use output devices to show the bit pattern, or simply a hex display to show 4 bits more compact. Now, next I want to show you how to use flip-flops for building something like a counter. What I want to have in this counter example is the following: a flip-flop where I can store 4 bits, and input device, a push button, which should have the following effect. Whenever I press the push button, this counter should be incremented by 1. The push button, recall, generates a 1 if you press it, and it has a value of 0 if the button is released. Now the idea would be to use an adder, a 4-bit adder, and I simply will use the 4-bit adder from circuitverse. So let's change it to 4 bits. Then use B for the increment. I can use a constant input with 4 bits, and I can initialize it with 0, 0, 0, 1. So I connect this here with B. Then the sum is connected with the flip-flop, and the push button is connected with the clock. And the value stored in the flip-flop is used as value A for the adder. And then this first idea would be that if I press the push button, the following happens. I have here the value 0 connected with A. This gets added with this bit pattern, so it gets incremented by 1. And because the push button is probably still pressed, this result would be stored in this flip-flop. But now, of course, if you press this push button, you see this error message at the bottom: simulation stack exceeded, because you have a recursion. You basically store the incremented value, but because the push button is still released, otherwise you wouldn't get here an update. At the same time, or seemingly at the same time, this new result gets incremented again and again and again. You have an infinite loop. What you have to do is you somehow have to better control the information flow. You want to increment the value once, and then you have to release the button before you can increment it again. And the idea is to use actually two flip-flops. This flip-flop will be called the accumulator. Put this here at the top. And then I use some buffer, or I could call it register. And this register will be actually my counter. So I also could call this counter. And then I will also use a NOT gate in between the push button and this accumulator. And the information stored in the accumulator will be used as new data for this counter or register. So now you already see the following. Because the push button is not pressed, the result computed by the adder gets copied into the accumulator. It flows into the accumulator. But this value stored in the accumulator does not get copied into the counter or into the register. But if I press the push button, new results computed by the adder will not be copied into the accumulator, but the value stored in the previous time step in the accumulator gets copied into the register. So I press it now. Now I have the register updated by the value of the accumulator. Now I have the adder already computing the 2, but this new information does not go into the accumulator. So if I release it, this happens. So what you also might want to do is the following. Connect a 4-bit output field with the value that is computed by the adder, but not copied into the accumulator when you press the push button. Now you see I press the push button and this value computed by the adder is 0011, but the accumulator still stores 0010. Now I release it, and then you have this and this one here in sync again. But here you still have the old value. And by that you see pressing the push button increments the counter. So that's maybe call this here register / counter. What you also can play around with is another element. Let me find it. This clock here, which is basically just generating a sequence of ones and zeros with a certain frequency, and I can use this instead of the push button. Then you see the counter gets incremented with a certain frequency. And you also can change this frequency, I think here, and speed things up. But mostly we will use push buttons so that we manually can simulate something that is later in the computer used as a clock device, so that we can better see what is going on step by step. Okay, the next thing I want to show is how to build a memory device, a random access memory, by using flip-flops. And I will call this RAM for random access memory 4x4. Because it has 4 memory cells, and in each memory cell I can store 4 bits. Let me first set up the 4 memory cells. Each of them has 4 bits, and then I simply copy it a few times so that I have in total my 4 memory cells. And then I will call this memory cell the memory cell with address 0, this here the memory cell with address 1, and so on, address 2, address 3. And then I want to be able to store data in one of these memory cells. The data, of course, has 4 bits. So let's call this also data in. I also want to be able to read data from a memory cell to inspect what is the value stored in one of these memory cells. So this is output field with 4 bits. Let's call this data out. Then I somehow need to specify from which memory cell I want to read the value stored in it, or to which memory cell I want to write this data in. For specifying what memory cell should be addressed, I need 2 bits for addressing 4 memory cells, and I also will call this input here address. And then I also have to somehow select whether I want to write something to a memory cell or read from a memory cell. So for that, 1 bit is sufficient, and I call this write. And now I do the following. I first connect this data in with each of these flip-flops on the input side with the data input port, and that's simple. Now, in order to actually copy or move this data into one of these memory cells, I simply have to activate the corresponding block of the corresponding memory cell. And what memory cell actually is the corresponding memory cell is selected with this address. And now I can use a demultiplexer where I will have on the input side a clock signal, which basically will be identical with the value of write. If write is 1, it's meaning that one of these flip-flops should be activated for writing. And in order to select 4 of them, I have to change the control signal size to 2. Okay, now I have to do this here again. So, for example, now I'm activating here the port with label 2, and with that I would activate the port with label 3. So now I simply connect this ports here, this port 0 with the flip-flop with address 0, and so on. And then I already can play around with that. For example, you saw that it already has modified the value stored in this last flip-flop, because write was equal to 1, and the address is 1, 1. Now let's say I want to write hex 3 into this memory cell. It has the address 0, 0. I change this here to 1, and then this data gets copied to exactly this memory cell. I change it back to 0, change here the bit pattern. Now I want to write this bit pattern to this memory cell. It has the address 1, 0 or 2. So I change here the address. I change this here to write and go back. Then I can modify again the address. Now I'm addressing this flip-flop here. Change the bit pattern so that we see some effect, and I now can specify where I want to write this data here. And for reading from a particular memory cell, the content, I will do kind of the opposite. I will use a multiplexer, also with 2 bits control size. I use the same address for activating one of these input ports. And then, of course, I should also change the bit width of this multiplexer to 4. And now I think this is just a circuit verse that this is still red. You see now everything is fine again. And then I connect the queues of the flip-flops with this input side. But only the addressed flip-flop actually delegates the information to this data out. So if I want to inspect this flip-flop, I simply change the address to 1, 1. And here I don't have to use write or data in if I simply want to read the things. Okay, and that's already nice. And on top of that, I want to now create a larger memory device, or a memory device where I actually can store at a certain address a complete byte. Now, 4 bits are also called half bytes or nibble, and I want to store at a certain address more information, 8 bits. That's what we actually need for a computer where you can run C programs. Now that means I will use this here as a black box from now on, and that means when I use this as black box, I cannot see what is in each of this memory cell actually stored. I will only be able to inspect from one memory cell the stored value. And this is okay for actual applications, but for education and for debugging, it's good to also be able to look inside some types of to look inside this black box. So I will also use some debugging outputs, 4 bits each. I call this here D0, debug 0, and this should, for example, show me what is stored in this device in the memory cell with address 0. And in a similar way, I want to be able to inspect what is stored at address 1, 2, and 3. So I copy this 3 times. Call this here D1, this here D2, this here D3. And then I patiently connect this with the correct flip-flops or memory cells. Okay, and then we check the layout, and for example here the width might be more usable in this size, and I think it's okay that the debug outputs are here at the bottom, because I later can connect these here with hex displays. Okay, and now I save this, and next I want to show you how to build a random device with 4 memory cells, and in each of these memory cells I actually can store 8 bits, so I call it RAM 4x8. Now of course I could use again flip-flops, change the bit width to 8, use 4 of them for building a 4x8 memory device, and actually this device should behave as if I would have done that, but in reality I'm a bit lazy. I want to reuse what I already have built, and the idea is that I should be able to simply use 2 of this 4x4 memory blocks and store the upper half of 8 bits, for example in this memory block, and the lower half in this memory block, always at the same address. And you will see how this actually works by simply doing it. I take here 8 bits. This didn't work. 8 bits. That's my data in. I will have a address with 2 bits. So let's change this here to address. And the bit size to 2 bits. And also, as before, a bit for selecting whether I want to write or read. Now with this data in, I also will use a splitter which splits 8 bits into 4 and 4. And then I do the following. The upper half, the high half byte, or the high so-called nibble, will be stored in this memory device at the address that I specify here. And the low half byte will be stored in this memory cell at the same address. And whether I want to actually write something to memory or not is in both cases also the same. So I will use this write signal twice and connect each of these memory blocks with the same write signal. And then of course I also can use this splitter again for reading 8 bits. Let's change the direction. From memory, from a particular address. And for that I simply connect the upper half of this 8 bits with data out here. I will need here a bit of space so that I later can make use of this debugging outputs. And now you see the upper half comes from here, from the address specified here, and the lower part from here. And then I connect this with an 8-bit output. And this is actually already working random access memory with 8 bits that I can store in 4 memory cells, or it's acting like that. But let's inspect actually what is going on inside. The byte stored at address 0 comes from this memory block and this memory block, and I actually can connect here this outputs with this 2 hex displays. And then you, for example, see here at address 0, I currently have stored this value because write is on 1. If I change this here, I'm having 1 byte stored at address 0, but the lower part actually just comes from here and the upper part from here. If I change it here again, so then you see that this hex 3 comes from here. And in a logical view, this here is the byte stored at address 1, but half of it is stored here, half of it is stored here. And like that, I want to illustrate this a bit better by doing this here 4 times, which will take a bit of patience. So this here is, for example, the byte stored at address 1. And I have also here the high part coming from here and the low part coming from here. And here I currently have stored a 0. And like that I connect all these memory cells with these output devices. So that's the high nipple from address 2, from address 3. Then I need this once more. And now the wiring becomes a bit of a challenge. But feel free to do this nicer. Okay, and now I also want to use some labels. So this here is address 0. I will use decimal notations for that. This here is address 1. This here is address 2. And this here is address 3. Now I can get rid of this here. And now let's say I want to store here hex F, hex 3. Then I first change write to 0 so that I have some time to modify it. So I set here the high part should be an F and the low part a 3. And I want to store it in this memory cell with address 3, so I select the address as 1, then I change to write, and here we go. Then let's say I want to change this here so that I have at address 1, hex 2. So I change here the upper part to hex 1 and the lower part to hex 2. Change the address to 10. I want to change this here. Bam. And let's say I want to change this here to hex 3, hex 4. Then this here is 3, this here is 4. The address would be 10 for address 2. And here we go. Now, if I simply want to get here the value stored at a certain address, so for example 3F, I select address 00, and then you see hex 3F is 00 and then just once. If I change the address to 1, I get the bit pattern for hex 1, hex 2, and so on. So we have the possibility to copy 8 bits to a certain address, so that it seems as if I would have 4 memory cells, and each of this memory cell can store 8 bits, but the realization is actually done by splitting this data into 2 parts and storing half of it here and half of it here, but always at the same address. Now the next step would be, now we have a memory where we can address single bytes, which is good enough for a computer, but 4 bytes that I can store is not so much. Let's change it so that we actually can store 8 bytes. And for that, again, it would be nice to have a way to actually look into the memory. So what I will do in some break is the following. I replace this hex displays with some output fields so that I can actually reuse this circuit. And I also will call this here, for example, data out. So back in a second. So I'm back, and you see I cleaned up the mess a bit. I removed all these hex displays and this wild wiring. I now simply have 4-bit output fields for inspecting the content of this memory cell stored in this block and this block. And also this indexing indicates what information you actually see. In this memory block, I'm storing the upper, the high part, the high half byte of a byte, which is indicated with this 1, with this first digit after D, and with the second digit I'm indicating the address of this memory cell. And here, because I'm storing here the lower parts, the low nibbles, it begins with a 0. And now check out the layout, because you will see that here, if you have it like in my case, ordered like that, it's not that good for later usage, because, for example, here I have the high nibble of the memory cell with address 0, and here I have the corresponding lower part, the low nibble of this memory cell with address 0, and I would like to have them next to each other. So I will rearrange that so that I have 1000, 1101, and so on. Now in a real memory block, you just would have this inputs, data in, address and write, and just this output, data out, and this here is just for demonstration purposes. And now I save this. And with that I begin the next circuit for an 8x8 memory block. So I have 8 memory cells, and in each memory cell I can store 8 bits, or at least it behaves as if I would have something like that. Now, of course, the idea will be again that this memory device acts as if I would have actually 8 memory cells, where each memory cell can store 8 bits. But in reality, I'm simply using this last memory device twice. And I will show you how this works. I have 8 bits for the data that I eventually want to copy into a memory cell. And I have an address with 3 bits, because I now can address 8 memory cells. So this didn't work. So this is the address. And actually I want to have the address here. Now the idea will be, if the address has a most significant bit of 0, then the value is something from 0 to 3, then I only will use this memory block. If the most significant bit is 1, the value is something from 4 to 7, and then I will use this memory block for either storing this data in or reading data into a data out, which I already can prepare. So this will be data out. And that means with this most significant bit, I somehow can select whether this device or this device should be used. And that calls for a splitter, where I split 3 bits into 2 and 1. And then you see here with this bit here, that's the most significant bit, I can select between these two memory devices. Now 0 will mean I want to have this one here. And 1, I want to have this one here. Data in, again, will be connected with both memory devices. The least significant part of this address, what I have here, will be used as an address. And the write signal goes either to here or here, depending on the most significant bit of the address. And for that I use a demultiplexer, where I connect write with the input. The control bit comes from the address, and this write goes to here if the address has a most significant bit of 0, and otherwise it goes here. The data out comes either from here or here, also depending on the most significant bit. And here I will use a multiplexer with 8 bits of a bit size, and the control bit comes from here. Now, if the control bit is 0, like now, then this here should be connected with data out from here. And it also should get the information from here, and otherwise from here. And that's actually already it. Now, of course, for actually seeing how things are organized, we should use a few hex displays to actually see what is inside of this memory block and this memory block. And so, for example, I should connect this here with here and this here with here. And again, I will simply do this in a break. You already can do this in the meantime by yourself. Check it with my result. Okay, so this took some time, but now you see I have here pairs of 2 hex displays for displaying 1 byte stored at address 0, 1, 2, 3. And this first 4 bytes all come from this memory block. Then I have another group of 4 bytes with address 4, 5, 6, 7, and they all come from here. And now we can check whether our memory device actually works. Let's say I want to store something here, let's say hex 1F, then the value should be with this that I have to specify in data in. The address of this here is 011, and then I write this to here. And let's say I want to store something here. The address of that would be in binary 100. Let's say I want to store F1, so I simply change it here to this bit pattern. I hit write and back. And then you can play around that you can write data to each of these memory cells of a particular kind. So I will simply do this for a few arbitrary bit patterns. For example, here I want to change something, and so on. And then you also can check that if you set write to 0 and leave it 0, you can inspect here with the address field the content of this here, still 0. The address, the content of this byte should be the same here. Here, of course, for data out, you also can use hex displays, but validate that this here is hex 5, and so on. So you can write bytes to a certain memory cell and read from a certain memory cell a byte. For the assignment, and we can of course do this together in class, we want to build an additional device, a loader control, which allows us to initialize a memory with a sequence of certain bit patterns. You see that I'm here simply using this RAM 4x8 block, so I'm just demonstrating this for a memory with 4 memory cells and 8 bits, and this is also sufficient for the assignment. And I simply will now show you how this device can be used for initializing the memory sequentially. I first select here a certain bit pattern. So this would be, for example, hex FF. Press this button, and this should initialize the first byte, the byte with address 0, with hex FF. Boom. Then I'm changing this bit pattern, so this should be hex AA, and if I press this button again, it should initialize the next memory cell, the memory cell with address 1, with this bit pattern hex AA. And if I change this bit pattern again, then pressing this button should initialize this memory cell. And now the other button, the reset button, will allow me to redo this, to again begin initialization at address 0. So if I change this bit pattern here to something, press this button, it should again initialize the byte at address 0. And later we will use this feature for initializing the memory with a program, byte by byte. Now, of course, you might guess that building this loader control is actually the essential part. And you also might guess that using a counter together with these D latches might be one way to implement this loader control. And of course, in this case, this counter will be just a 2-bit counter if we use this 4x8 memory block.